I wish to thank the organizer for inviting me to give this talk. So today I will talk about homological mirror symmetry for theta divisors. This is based on joint work in progress with Haniya Azam, Catherine Cannizzo, and Heather Lee. So I have to confess that I don't know much about homological mirror symmetry, and my co-authors know more. And also, I just heard this talk by Gabriel, and I realized the first part is, so his talk is a much more expanded version of the first part. But so I will try to go through this quickly. So first, so theta divisor is the hypersurface in an abelian variety. So first, let's briefly review mirror symmetry for hypersurfaces in C star M. And then the first part will be an overview of mirror symmetry for hypersurfaces in abelian varieties. And then the point of today is that we are trying to do it over complex number instead of over Novikov field of Novikov ring. So there might be constraint about which objects one allows. And the last part is about global homological mirror symmetry over the complex moduli. There aren't so many examples where you can understand the complex moduli globally, right? Principally polarized abelian varieties is one of such examples. And yeah, please feel free to interrupt. I like many of you know this much better than I do. Okay, so first, so I'll just follow these two papers. So of course, they do mirror symmetry for hypersurfaces in much greater generality. So I'll just briefly recall again the case when the ambient space is C star N, following up, say, AAK is say, Aglu and Karzakov. So the data it appeared in arXiv about 10 years ago, and then last year, Abzey and Aglu's paper finally appear. So yeah, the notation might be slightly different, sorry. So we take a hypersurface in C star N is defined by, so it's called H, and it's a zero locus of a Laurent polynomial. So it has finitely many terms, and we will like, so this M is a lattice, it will be the co-character lattice of this C star M. And so then, as we just reviewed in the previous talk, so if we do a tropical light, so F defines a holomorphic function from C star M to C. And if one tropicalizes it, one gets a piecewise linear function from Rn to R. And this Rn is actually M tensor by R. So then we consider this moment. So this will be the moment polyhedron. Yeah, it's non-compact, so its polyhedron is instead of polytope of some symplectic toric Calabi M+1 fold, and we would like to make sure the coefficients are chosen nicely so that you get something smooth. So now the the polyhedron determines the symplectic structure, but we can also view it as some GIT quotient of Cn +1 plus k by the action of C star k. And in this presentation, you remember the holomorphic structure. And the superpotential is just like, if you take the product of all the coordinates, because of the Calabi condition, C star k preserves it. It descends to the superpotential, which is a holomorphic function on this non-compact M+1 manifold. And then this will be the so this y comma v will, as we see, it will be the so-called generalized SYZ mirror of the original hypersurface. And on the other hand, the original hypersurface can be realized as the critical point of some superpotential also on some M+1 dimensional complex manifold. More precisely, one takes C star M cross C and blow up at H cross 0. And there's a projection to C star M cross C. And then we project with second vector. And then this composition is a superpotential, which is a holomorphic function defined on X, whose critical locus is exactly H. So I think this generalized SYZ can be viewed as some version of Landau-Ginzburg Neurosymmetry. But now, because since on the left-hand side, the critical locus is smooth and is equal to H, so the left-hand side can also be replaced by this hypersurface. Well, this is my naive understanding. So my understanding is AAK mostly discuss A model on the hypersurface and B model on this Landau-Ginzburg mirror or generalized SYZ mirror. And they and whose most recent, their recent paper last year is more about B model on the hypersurface and A model on this toric Calabi-Yau M+1 fold together with the superpotential V, which is the product of all homogeneous coordinates. So if we consider B model, if we view it as this Landau-Ginzburg model, and the category should be the DG category of matrix factorization. But because critical point is smooth and is equal to this hypersurface, so it's a DG category of perfect complex on H. And on the other side, on the A model side, one consider the Rapp-Foucault category of this Landau-Ginzburg model Y comma B. And as a consequence, we get a derived version. So in their paper, they do this DG and A infinity version. But yeah, that's beyond my own ability. So today we will mostly focus on this version, just the bounded derived category of coherent sheaf of H. So there's also, so you see, like I usually count Gromov-Witten invariants and open Gromov-Witten invariants in case where there's some mirror formula. So I usually work over C because there are explicit mirror formula, and you see that they actually have some positive radius of convergence. And so this is what, so Chen, Chao, Lau, and Zeng. So this appearing archive in 2013. They do SYZ mirror symmetry for toric Calabi-Yau orbifolds. So manifold, and they also allow orbifold singularities. And so they prove an open version of Ranz-Kreppen resolution conjecture. Basically, the generating function of open disk invariants, how they change under birational Kreppen. These are all like Calabi-Yau. So they are all related by Kreppen transformation. And in this case, they are like they consider like two Calabi-Yau orbifold. One is the partial Kreppen resolution of the other, partial toric Kreppen resolution. I always wonder, is it possible? I mean, maybe you have opinion. I wonder, like, is it possible to like do, because we know like there in like genus, for genus 0 closed Gromov-Witten invariant, there's global mirror symmetry over the secondary. The block is secondary toric variety, which is a toric variety defined by the secondary fan. And it can be viewed as the complexified Kähler moduli of the toric Calabi-Yau manifold or orbifold. So that's a question. Okay, so but now today we are trying to do similar thing for hypersurfaces in abelian varieties. Okay, so this is, so I still follow this. There's a section 10.2 in this paper, and they say this is suggested by Paul Seidel. So follow their construction, and so as before in that paper, they mostly focus on A model on the hypersurface. and B model on this Y comma V. While in like Cannizzo's 2019 PhD thesis, he focused on A model on the hypersurface. In the case when it's actually a abelian surface, so the hypersurface is actually the theta divisor is a genus 2 curve embedded in the abelian variety. Its abelian surface is also the Jacobian of the genus 2 curve. So what she does is she does it for some one parameter family in the complex moduli of genus 2 curves. So in the work in progress, like Azam, Cannizzo, Lee, and myself, so first try to do it for like abelian surface and for the whole complex moduli. And then also we want to consider higher dimensional abelian variety. A priori, one can consider other hypersurfaces, but today we will just consider the theta divisor. So V tau is an n-dimensional principally polarized abelian variety. So the coordinates are Z1 to Zn. So quotient by lattice Zn plus tau Zn, where tau is a point in the single upper half space of genus N. So it consists of, it's a space of n by n symmetric complex matrices such that the imaginary part is positive definite. Sometimes it will also be convenient to view it as like, so first quotient by the action of Zn, then you get C star n quotient by gamma. Then the group, the lattice will act multiplicatively. So we, let's see, so yeah, so there's this 2 pi I zj. So like the periodicity is zj goes to zj plus 1. Okay, so then in this example, the generalized SYZ mirror to the theta, this theta divisor, similar to the construction of hypersurface in C star n, is a Landau-Ginzburg model, Y comma V. Yeah, so as I mentioned, so AAK like consider in that example, consider mostly A model on the theta divisor. Also, they consider the case where the real part is 0 for simplicity. And today we will consider B model on the theta divisor. So the relevant category will be bounding category on the derived category of coherent shape on this theta divisor, which is now smooth and projective, and A model on the mirror Y comma V. So as I said, this is actually it's a real one-dimensional submoduli in the three-dimensional complex moduli of the genus 2 curve. So this case is considered in Cannizzo's PhD thesis. So okay, so now for some time I will just talk about really classical stuff like the work of Riemann, for example. So consider so first we will consider B model geometry and the complex moduli. So recall that the theta divisor depends on, so let's consider this universal theta function where tau is a point in the upper half, single upper half space of genus N. And now we use the multiplicative coordinates xi. So this is the theta function. And so this is so if we fix tau, this is a quasi-periodic in X. And this descends to a section on the V, so on the principally polarized abelian variety. And this L is the ample line bundle associated to the theta divisor, which is the zero locus of the theta function. And indeed, so recall that, yeah, the space of all section is just generated by this section. It is so this pair is a principally polarized abelian variety. And so in particular, if we take the first Chern class, it is in H11. Yeah, it's in the intersection of H11 and H2 with integral coefficient. Indeed, for general tau, this will generate like the neuron several group. So for generic point, tau in the Siegel upper half space, the Picard number of V tau is actually 1. And this first Chern class defines an integral symplectic structure on the first homology class. So let's recall that. So this Siegel upper half space can be viewed as the moduli principally polarized abelian variety together with a Torelli structure, or equivalently a choice of symplectic basis of the first integral homology class equipped with the symplectic structure given by the first Chern class of this principal polarization. And then if we forget the Torelli structure, which it's like so it's a principal, it's a covering space. And the deck transformation is SP, the integral symplectic group. And the action on let's see. So the action on tau is given by this. In particular, when n is equal to 1, this is the formula. In that case, SP2Z is SL2Z. So now, actually so because we are now want to do this SYZ neurosymmetry, it will be convenient to introduce some moduli space, which is between these two. It will be a cover of this moduli of principally polarized abelian variety. So let's do the following. So write tau B plus I omega, where B is just a real part and omega is the imaginary part. So this is notation. So SNR stands for symmetry real M by M matrix. And this PNR is the open convex open subset where it's positive definite. So the real part, so the real part in the rest of this talk, the real part will be B and imaginary part will be omega. B will be symmetric, omega will be symmetric and positive definite. So this V tau is, so now V tau is like complex torus. So we can consider, so there is this log map and the base will be a real flat torus. And so this imaginary part is positive definite. So basically the base of this SYZ figuration is just a flat, real n-dimensional compact torus together with this flat metric determined by omega. And let TF be a fiber. So now it will be convenient to consider this subgroup of this integral symplectic group where C is equal to 0. So what is this group? So this is the subgroup which so if we consider the inclusion of fiber, so the inclusion of fiber, the H1 of the fiber is a rank n lattice sublattice, which is actually Lagrangian with respect to the symplectic structure. So this G is actually the subgroup which preserves the subspace. So we can forget most of this Torelli structure, but we want to remember the subspace, which is the first homology of the fiber. Here are some classical basic facts. So first, this subgroup is generated by GL and Z, which is given by the diagonalized one, and also the symmetric. So the first group, if you look at the action, is like send tau to A tau A transpose. This is a GL and Z action. When n is equal to 1, this is the center and this action is trivial. And the second action is just translate tau by so this, you see, this only changed the real part of tau. It changed it by an integral symmetric M by M matrix. When n is equal to 1, this is just tau goes to tau plus 1. So this is our subgroup. And also, moreover, so the whole symplectic group is is generated by this subgroup and this single element. So yeah, so this yeah, so we consider this G and indeed consider this, and then together they generate the whole thing. So so from now on we will focus. Oh, sorry, I don't know. Right. So now we have this picture. Yeah. So we can first just mod out the action of this translation by B. Right. This has a compact torus, and then the the SNR part is the real part, and PNR is the positive definite part. It's the imaginary part. So HN is so this is something here Bn plus. So this is B and this is omega. And then so actually if we just there's a map, if you just take the imaginary part, so you just get this. This can be viewed as the tropical version of the Siegel upper half space. And we also saw a lot of tropical geometry in the previous talk. So then this first quotient by the action of this translation, and then so it has a map to G. And the moduli of pure tropical principally polarized abelian variety is simply you just take the space of, it's basically a moduli of flat real torus, compact torus of dimension M. And then so this covering space we introduce. Yeah, I don't know if someone knows there's a name for this G or a name for this moduli space. Please let me know, because I have to confess I don't know the literature very well. So today I'll just call it moduli space of principally polarized and SYZ fiber abelian variety. So taking the imaginary part defines a map to the moduli of pure tropical principally abelian variety. So what is map? So this just sends your principally polarized abelian variety to the base of the SYZ fibration. So there are literature of this tropical principally polarized abelian varieties. This is probably not complete, but Catherine, Haniya, Heather, and myself, we read papers by these authors. So then if we have, so now we have this kind of picture. So over this tropical, so over this we have universal pure tropical principally polarized abelian variety. And then we can pull back, and then over this ANF, the moduli space we introduce, we have this universal SYZ fibration, where V is the universal principally polarized abelian variety. Yeah, so for each point is we take a point, and then the pi SYZ is given by this map. Okay, so now this is a B model. So what we are going to do is over this so we want to construct do the generalized SYZ mirror construction first over the whole Siegel upper half space, and secondly see that this GX actually acts on the universal family, so it descends to a universal family over this AF. So we will identify this PNR with the Kähler space of the generalized SYZ mirror. And so if you include, and this will be so this is just equal to PNR. And this is complexified Kähler space of Y. And And then this is before you just quotient by the action of the translation by an integral, symmetric, and by a matrix. And we want to say that, so the pure tropical, principally polarized abelian variety can be identified with the Kähler moduli. And yes, and then the moduli space we introduce, which is a cover of the moduli principally polarized abelian varieties, is the complexified Kähler moduli of Y. So I think we can actually, so then we will study the decomposition of Kähler cones, but today we will just focus on the, like when n is equal to 2, yeah, because otherwise it's very difficult to draw this. And so actually, so it's actually coincide with the Voronoi decomposition in this paper in 1908, so more than 100 years ago. So now let's do this construction in greater detail. So yeah, take a point in the Siegel upper half space. The real part is B and the imaginary part is omega. And we take this theta function and take the tropicalization, and we get this polyhedron. So when we do this in the C star n case, so we get the polyhedron with finitely many facets, where the number of facets are in one-to-one correspondence with the term in the Laurent polynomial. So now it's a series. So there are infinitely many facets. We get one for each lattice point in Zn. And there's some condition. So basically, what is the chamber structure? Because there are some condition such that we actually get something which is smooth. So because there are like infinitely many facets, and so we get from this facet, we get a fan which is infinite, and so we get this one y tilde is toric Calabi m plus 1-fold. Moreover, because the original theta function is quasi-periodic, so this infinite fan has an action of Zn. So if
can you say again what the notation was? Sn and Pn?
Oh, Sn is the m by n symmetric matrix, and Pn is m by n symmetric and positive definite. Yeah, so after tropicalization, this polyhedron only depends on the imaginary part. So for a while, the construction only depends on imaginary part. So first we want to construct the mirror as a complex manifold, and the complex structure only depends on the imaginary part. So first we construct this y tilde, which is a like toric Calabi m plus 1-fold, but of infinite type. And still we have this, not because there are seems to be infinitely many coordinates. So but still we have this this superpotential where in each Cm plus 1 chart, it looks like the product of all coordinates. And because of this quasi-periodicity condition of theta, so there's a Zn action on the fan. Yeah, actually when n is equal to 2, we can draw it. So we know that if you have like an isomorphism of fan, then it induces some so Zn is the automorphism of the fan. So if we have an automorphism of fan, it will induce automorphism of the toric variety. In general, you have a morphism of fan, and it will define a toric morphism. So this Zn action, well, it's not free over the whole thing, but if you just take the, say unit disk in C and look at the pre-image, then the action is free. So one can quotient by this action. So now like y tilde is like simply connected, but yeah, so y tilde and So the SYZ mirror as a complex manifold is defined by this quotient, and because the superpotential is Zn invariant, so it descends. So now the next thing is one wants to construct a Kähler metric on this thing, which is, so the idea is we take this y tilde prime and we construct a Kähler metric which is invariant under the action of compact torus, and also invariant under Zn. So this was done by Cannizzo. So we use construction like they use, so we get a Kähler form. But okay, so before the quotient, so the generic so outside zero, this is a smooth vibration. So before we do this quotient, the fiber outside zero is just C star n, and after one do the quotient, the fiber becomes a compact torus, which is dual of the original torus, V tau. So we have this picture. So so the Kähler form is only like is defined on an open neighborhood of the singular fiber, which is a fiber over zero. So we might need to shrink this a little bit more, but now we get this. So now with this Kähler structure, this is not only a holomorphic vibration, but also a syncretic vibration. And so there's a moment. So y prime, there's a moment map. The first n coordinate is denoted by c, and the last coordinate is eta. And so y tilde prime is the universal cover of our mirror y, and it maps to this it maps to the space T omega. And if you restrict to a smooth fiber of the superpotential, we get a dual SYZ vibration. So this is the mirror picture. So now, up to now, so as a Kähler manifold, this only depends on the imaginary part of tau that we started with. So now for the real part, which is B, so we use this to construct U1 n+1 invariant Z and invariant closed to form, and this will be the B field. So now we get a complexified Kähler form, and this is called Y tau. So using this tau, we define this this Y together with a complexified Kähler structure. And the complex dimension is, yeah, so this is the same dimension as the dimension of the principally polarized abelian variety of dimension n. So this is so the Kähler moduli is n+1 over 2-dimensional. Well, so this is just an interesting remark. It's just, yeah, if we look at the fiber, so say we take Q, which is in puncture sphere, say very small non-zero complex number, and look at the pre-image of superpotential is C star n, and we look at the action of this Zn, and this dual thing actually as a complex manifold, it's a cell product of the same elliptic curve with modular Q. So it's like this complex moduli is one-dimensional, and it's parameterized by the base of the superpotential. And then, so for a generic Q, so the Picard, so the intersection of H11 with the integral classes H2 is actually this. So this rank is a dimension of the Kähler moduli. Okay, so now I want to focus on the two-dimensional case where we can study the Kähler cone of Y. So now in the two-dimensional case, the theta divisor is the genus 2 surface, and Y will be a non-compact toric clubial, non-compact clubial threefold, and the universal cover will be a non-compact toric clubial threefold of infinite type. Okay, so in the two-dimensional, so this is the uncomplexified Kähler space, the space of Kähler structure. So it's just, yeah, so I just want to rewrite this. This is the space of symmetric 2x2 matrix, which are positive definite. So instead of using omega ij, we use 3 parameters x, y, z in this way. And then the condition of that being positive definite is exactly like this interior of this cone. So, and also because it's a cone, so I mean, to understand the Kähler's, yeah, so to see the Kähler cone, we can just take the cross section like when z is equal to 1, and we can get the cross section. So for example, this phase 1 is, okay, so let me look at this picture. So this is a picture like before the quotient. So yeah, let's see. So before the quotient, so what I draw, so what happens is the following. So we take this cone and we intercept this cone at, so actually it's a union of infinitely many Kähler cones, and we take the cross section when z is equal to 1. So the whole thing is a circular cone with interior, and each Kähler cone is a triangle cone where all the vertices are on the boundary. So in this case, this is before the, so this is just the Kähler cone, right? There's no, it's just the uncomplexified Kähler structure. And then if we mod out by the GL2Z action, all the 3-dimensional cone are in the same orbit. Moreover, there is like S3 axon 1 of the cones. If you look at the stabilizer of GL2Z action on this, the stabilizer of one cone is like permutation group of 3 elements, and it will permute the 3 walls. So all the so for example, the first chamber, so in this coordinate, so if we, so this is the, we now want to interpret as a Kähler moduli. So in the first chamber, so we have, let's see, so we have the slope 1 sphere, which, so the sphere, the blue spheres are identified under the Z2 action, the red spheres are identified under the Z2 action, and the green spheres are identified under the Z2 action. So on the universal cover, we have infinitely many spheres, and the quotient, we have this configuration of bananas. So we have a green banana, red banana, and a blue banana, and they correspond to this lines in the palatal picture. So this is, so if we consider the moment polyhedra of the toric clubial threefold of infinite type, and then we project it down, and so we get this, so we just get many hexagons. And then so below the hexagon picture, so there are like infinitely many hexagons before the quotient, and then below this picture is the fan picture. So let's try to do some wall crossing. For example, so in the first chamber, so the diagonal terms are the symplectic area of, so we know that the uncomplexified Kähler parameters in this chamber are just given by the symplectic area of these 3 spheres. yeah, and in the first chamber, so the off diagonal term is like the area of the blue sphere, and the 1 term is the area of the first and the second sphere. And now let's see what happens if we let one of the sphere goes to 0, say the blue sphere, which is the first sphere, then it will cross to the second chamber. And then similarly, if you let the red sphere, which is the third sphere, goes to 0, it will cross to the fourth chamber. So let me show you this wall crossing picture. Yeah, so this is what happens. So you have this polytope, and then as you as you cross the wall, so at the wall, the off diagonal term, which corresponds to the synclitic area of the blue sphere, goes to 0, and you get a rectangle instead of a hexagon. And after that, then the slope of the blue sphere becomes -1. And also you see that in the middle, what happens is you just have conical singularities, and after quotient, all the conical singularities become the same point, which, yeah. And so similarly, we can do the wall crossing from 1 to 3 and wall crossing from 1 to 4. So in this case, yeah, they are all isomorphic as complex manifold. In higher dimension, the fact is we can consider this GONZ action. There are finally many orbits. So in higher dimension, you can get Clavial n+1 fold, which are probably not isomorphic, but birational to each other. But there are only finally many of them. Okay, so finally, I think, yeah, so after we set up the stage, so we are going to consider global holomorphic neurosymmetry. So yeah, I need to ask for, in particular, Kenji Fukaya about how to formulate this correctly. So the picture is the following. So the left-hand side is the homological neurosymmetry for abelian varieties. Polishuk and Zaslow did it for elliptic curve, and Kenji Fukaya about 20 years ago already did like the most general setting and the A infinity enhancement version. And now, so what we want is the right-hand side. So we have the top horizontal arrow is given by just pull back by the inclusion. I is the inclusion from the theta divisor into the abelian variety. And then, so now what is, yeah, so now one needs to understand the bottom arrow to the right. So the right-hand side, so this is the homological neurosymmetry for theta divisors. So Cannizzo did it to the two-dimensional case, or equivalent theta is a genus 2 curve. So we study the all dimensional cases. Oh, so the fact is, so yeah, actually the objects we consider are line bundles which exist for, so as we know that for generic tau, any line bundle is of the following form. So first, if we consider this, so if you have any z which is a point in the abelian variety, we can translate it and tensor the inverse. This actually will give us all the elements of the Picard zero. So for generic tau, any line bundle is some power of this principally polarization times an element in the Picard zero. And this is the object that we will consider. So so the top is So we have explained the top is like case power of L and shifted by Z. And we can restrict it to the theta divisor. And now let's consider the bottom. This will be so little l will be little l hat will be an object in the dual abelian variety, and capital L hat will be an object in this Fukaya-Seidel category. So this omega is in the action angle coordinate of the symplectic form on the Calabi-Yau threefold. It's given by this. So in this coordinate, so when we restrict to the fiber of the superpotential, so d eta is 0. And then we will use this r coordinate, which is like so this r coordinate are so we know that the fiber V check is diffeomorphic 2n dimensional compact torus, and this r and theta are like the integral coordinate. So the action of Z2n is given by theta goes to theta plus 1 and r goes to r plus 1. And then, so basically, so recall that, so this we just follow the previous work. So this is a linear Lagrangian, and the shift Z can be written as A plus tau B. So the mirror object B will give us some shifted this shifted linear Lagrangian, and K is the slope. And then this A will determine a line bundle with unitary connection whose whose curvature is the restriction of the given B field. Oh, so now, the diagram will just like send the objects in the blue boxes. So now I just need to explain the last blue box. So the last blue box is the following. We just take a fiber. So we just take this object on the dual abelian variety, which like is linear Lagrangian together with the U1 connection, just do parallel transport along this U-shaped thing in D. So basically it's diffeomorphic to a compact torus times R. So now we want to consider morphism. So recall that from on the B side, we have morphism between line bundles. So these are just the, so we can move the line bundle to the right-hand side. So it's just so sections of, it's just the cohomology of this line bundles. And then on the theta divisor, we just get the restriction of this line bundles. And we have this short exact sequence. So basically the theta is the, theta defines the, so the theta divisor is the theta divisor is the zero locus of theta. So we have this, this short exact sequence of sheaves on the abelian variety. And this, so this is roughly the idea is this. This is most, it's most clear when when, for example, if K2 is greater than K1, then somehow we just get, like this line bundle is ample, we just get H0. So this is just like we get H0 of L to the some power twisted, and then when we restrict to the theta divisor, so we theta divisor defines the ideal associated. Theta function defines the ideal of the theta divisor. Sorry. So and then let's look at the corresponding picture. So we know that so this capital oh, so first of all, we look at the so curly L is in the is line bundle on the abelian variety. So now we have this. We first consider object in the Foucault category of a dual abelian variety. So this is just the floor homology, but in this case, so it's generated by the intersection point. Let's consider first the case when K1 is not equal to K2, so they just intersect transversally at finally many points. And then the differential is, yeah, it's by counting bigons, but in this case, the differential, okay, let's for simplicity, let's consider the case where like say K2 is greater than K1, then the differential is just 0. So this is, and then on the other hand, we have home in the Fukaya-Saito category, which are given by which are given by the floor homology between these two objects. And you see the the bottom blue line is mirrored to the upper blue line. So basically, this is, so if we think like the most simple case where the upper line where actually K2 is equal to, K2 is greater than K1, and you have no H1. So basically this says H0 of the, yeah, of this. So the space of section on the theta divisor is the quotient space of section. And the bottom line is a similar thing. So now, so finally we have this diagram. So like the vertical, the vertical in the arrows in the middle and on the left, because the Kenji already proved the isomorphism. And then we just need to say that this diagram, if we can show that this the left square commutes, then we know that the right arrow will be an isomorphism. Yeah, and they commute by the Leibniz rule. So yeah, okay, so this shows some version of homological mirror symmetry for theta divisors. But the thing is, we really want to do it over the complex field so that we can do this globally over the classical moduli, over the field of complex numbers. But yes, but now there are some problems, because you see, like if we want to yeah, just this version. Of course, like this, like we just have this very nice, it's over this moduli space, and this G action, this module group just acts as like isomorphism from 1,5. So if we just before quotient by the symplectic group, so we have this thing on the single upper half space, and how does the symplectic group or the subgroup G of the symplectic group act? It sends the fiber, like on the complex side, it sends fiber of a point to isomorphically to the fiber of another point. So but yeah, the problem I think is this Foucault-Saito category. There are like other objects which are not linear Lagrangian. So those, yeah, we don't know if like this we don't know if we want to say the MK of general object which are not linear. We don't know if we can define it over the complex field. Okay, so yeah, I think I'll stop here. Thank you for your attention.
So if you want to question, then today, let's talk about this in 2 minutes.